So this is the second code, and you can see that up to 77, this is really the same one. So this is the same code as before for solving the very simple Laplace problem. And after this, we just have this small snippet, which is doing the eigenvalue solving. So we are using SLEPc eigensolver. So the first step is to initiate our matrices as PETC matrices, because SLEPc is part of this PETC library. So first part is just to create this matrix and assemble our BF. So what is BF and what is MF? So these are just our stiffness matrix and mass matrix. Okay. So this is the stiffness matrix which we built for our Laplace solution, right? Dot of these two terms. And what are phi and what are v? These are just the trial and test functions. So dot of the gradient of trial function and the gradient of test function, that's just your stiffness matrix for your Laplace problem. And this is the mass matrix, which is just trial function into test function, and you are again integrating that. Okay, so we have to remember that when the functions are orthogonal, then this mass matrix can give you 1, right? Basically, it's an identity matrix, which means that if these are orthogonal and they are normalized as well, so just when you multiply them and when the same indices are multiplied, they will give you 1, and when the different indices are multiplied, they will give you 0. So by multiplication, I am meaning the dot product here. In our textbook cases of our the Sturm-Liouville kind of problem, so we typically see these kind of formulations, right? So where x is our unknown, right? So we see these kind of formulations. And that is because in those cases the mass matrix is just the unit matrix. So in our case we have this kind of a system, right? Because in case of finite elements, the linear hat functions which we are using, or even the higher order Lagrange functions, so these will not give, so they are not orthogonal, so the mass matrix will not be unit matrix. So that is why we have to explicitly calculate this mass matrix, and then we just have to initialize it here, right? As PETC matrix, assemble it, then you just impose the boundary condition, the same kind of for loop as before, and then you just run the eigenvalue solver. So this is just piece of syntax. We have just chosen how many eigenpairs that we want to return. So the solver will just give us those number of eigenpairs, and then we just do the solution. So this is just some syntax, and really nothing much to explain here. And these are again your plots and diagnostics. So really very simple snippet. So let's just run this code. So this is our Laplace problem once again. Now you can see that these are our modes, right? Our lambda values, and you can see that they are very nice and well behaved, and that is because we are just dealing with a symmetric positive definite system, right? And these are your eigenvalues, right? So these are basically global vectors which are orthogonal to each other, which means that if you normalize them and you take the dot product, you will again get your Kronecker delta kind of property. And so this is what we'll use to construct a reduced order model. So now let's just go to the next code where we'll see the reduced order model. But for that, for this reduced order model, we'll make the problem slightly complex. So we'll just add a source term, and we'll keep it a linear source, which is just varying slightly with maybe x and y directions. And we'll just try to model this by using a reduced order model. So we'll just start off on the whiteboard and just show that process, and then we'll just go to the actual code so that it will become clear what are the meaning of those the lines of the snippet which we have added.